Last video today, part 8.4, variable size reduction. All right, so the problem we want to look at in this video, it is a special type of divide and conquer. In the previous video, when we work on factorial problem, we divide the problem by reducing the problem size by just 1. Yeah. In that Tower of Hanoi problem, we also reduced the problem size by just 1. Yeah. From n to n minus 1. Yeah. So you can see that is a pretty popular way to do the divide and conquer. Yeah. In our textbook, it calls this special way decrease and conquer, because you just decrease the problem size by 1. Yeah. But in my opinion, I still like to call it divide and conquer, because that is the most popular name. Yeah. So if you call decrease and conquer, people may not know what is the exact meaning of it. Yeah. All right, but we know that decrease and conquer corresponds to a special subcategory of divide and conquer. Yeah. In this video, we will look at another subcategory. We still do problem size reduction, but every time when we reduce the problem size, the size varies, sometimes large, sometimes small. So variable size reduction. All right. The problem we want to solve, problem number 10, greatest common divisor. Yeah. So let's look at the problem. Given two non-negative integers, m and n, so each greater or equal to 0, not both 0. So we do not allow m and n both 0. Yeah. Find their greatest common divisor, GCD, greatest common divisor of m and n. Yeah. First, the reason they cannot be both 0, because if you look at the GCD 0, 0, you can see not well defined. How do you define it? Okay. Yeah, because based on the meaning, greatest common divisor, what should be the number of GCD of 0, 0? You will see you cannot find any number satisfy that. Don't write 0. Okay? Yeah, because first, it cannot be 0. Second, because if you try 1, 0 is a multiple of 1, right? The second 0 also multiple of 1. So 1 is a common divisor of 0, 0, right? But it's not the greatest, because 0 is also multiple of 2, and so on. So you will see there is no way you can find the greatest common divisor if it's a 0, 0. Okay? That's why we call it not well defined. No definition for it. Yeah. All right, so from now on in our discussion, we will assume m and n cannot be both 0. Yeah. Next, first, how to solve it. Let's recall middle school procedure, because this problem is also very popular in middle school math. Yeah. The students are taught how to solve this problem, yeah, in middle school. Yeah. The steps used there, step 1, find the prime factorization of m. I hope you know the meaning of prime factorization. Okay? So write n as a product of a set of primes. Although one prime can be repeated multiple times, so use a power of prime to represent it. Okay? So in that form, prime factorization. Yeah. Step 2, find the prime factorization of n. So after that, step 3, find all the common prime factors, common. Okay, so the two you compare, so which prime, so it appears in both factorizations, and the power of that prime, what is the largest power of that prime, appears in both factorizations. Yeah. So then you take that. Okay. Number 4, compute the product of all the common prime factors. Yeah. So for those power of primes, several, the common part, multiply together, so you get a final answer. Yeah. Here, let me use a simple example to go through these steps. Yeah. 60. Yeah. So it's prime factorization like this. Yeah. Standard prime factorization. Yeah. 24, the second number, the prime factorization like that. Okay. Then we try to figure out the common prime part. Okay. For the prime 2, we figure out 2 squared is the common part. Yeah. So common factor for both prime factorizations, the common part. Yeah. 3, just 3. Yeah. So next we multiply these two numbers, so we get the greatest common divisor 12. Okay. So the answer is GCD of 60 and 12 is 12. Oh, yeah, right. Yeah. Oh, 24. Yeah. Sorry. This should be 24, right? Oh, yeah. GCD of 60 and 24 is 12. Yeah. All right. So that's the whole procedure for middle school math. Okay. All right. Here, the problem is solved. Why we do it here? Right? You may ask that question. There is one big problem in this solution. So can you see there is something not quite good in this solution? Right? Yeah. Because when we need to solve, we need to talk about all the possible non-negative integers m and n. And here we solve this problem for computer science. So not middle school. In middle school situation, the students usually, they are given two numbers relatively small. So the students can work it out on their papers. Yeah. But here in our computer science, we need to solve the general GCD for m and n. That means the general case here means these two numbers could be very large. Think about that. If these two numbers very large, is this method still, think about this method works well or not? Very large numbers. Yeah. Because in that situation, there is this prime factorization step will be extremely hard. Think about for a huge, big, giant number, how hard is the prime factorization? Yeah. Do you know there is currently the most important encryption algorithm? Currently there is the most popular, most important encryption algorithm. Yeah. It's called RSA. RSA. Okay. Yeah. Encryption algorithm. Yeah. So the algorithm is based on prime factorization, based on the difficulty of prime factorization. When you are given a huge number, so that huge number usually means thousands of digits. So think about that huge number. Then factorization is extremely hard. So you cannot do it. You cannot do it quickly, even using powerful computers. Very slow, because it is extremely difficult for large numbers. Then if your method relies on that difficult step, how can you solve it quickly? So this method won't work for large numbers. So we need to develop a method that still works even for huge number. For huge number, because we can use powerful computers. We can quickly find the answer. But this prime factorization, even you use supercomputer, you cannot find it quickly. Extremely slow, even by years. If you want to find it using this way, you need to spend many years to find it. That's not good. We want to use a few seconds to find the answer. So that's the main problem. All right. So now our new problem, a new algorithm to solve it. We do not rely on prime factorization. All right. First, let's look at a special case when one integer is 0, the other not 0. Okay, n cannot be 0. Then the answer is n. Okay, all right. Now let's look at the problem size, because when we do size reduction, we want to know what is the problem size. The maximum of these two integers. Remember, they cannot be both 0, so this maximum number is not 0. All right. All right. So for the problem size, so here, this is the problem size. Okay. So when we reduce the problem size, we reduce this expression. Okay. All right. How do we reduce the problem size? So that's the main idea for this part 8.4. So we will see it. Now, our goal, reduce the problem size for this part. To do that, we need a mathematical tool. We have to use some special mathematical tool to help us solve this problem. But that tool, pretty simple. So if I put it here, you understand it immediately. That's the division algorithm. Doing division, so you know how to do the division, right? Integer division. Here, so let me describe the integer division here. Given positive integers a and b, because it's positive, so then b is supposed to be non-zero. So positive. Right. How about non-negative? Right. Otherwise, we do not need. Right. Anyway. Small fix. So we can fix it. Small fix. There exists unique integers q and r. Q for quotient, r for remainder. With 0 less than equal to r, strictly less than b. B the divisor. Strictly less than b divisor, but we allow the remainder to be 0, such that a equals b divisor times the quotient plus the remainder. That's the division algorithm. For our case, because we use m and m, in order to make the discussion a little easier, we just assume m greater or equal to n greater than 0. Okay? For this case. All right. Here you can see both numbers not equal to 0. So that's why here we use the positive version. Positive version. Positive version definitely b cannot be 0. Because we already considered when 1 is 0, we have that answer easily. So we can exclude that. All right. So if we place m, n here, So we get this version. So we get this new version by applying division algorithm. Now we can use it to solve the GCD problem. So let's look at how do we solve it. All right. So we develop a key property, size reduction, the key property. How do we do the size reduction? This. Through transformation. We need to do some special transformation. Transformation on, on GCD. This formula we need to use in the transformation. But we do transformation on the GCD expression. So let's do it. GCD of m and n equals, we replace m by this expression. All right. Now let's apply the transformation formula here. Transformation here, I do this transformation. Okay. Fraction way division. This fraction corresponds to division, right? When I write that, I have the quotient. That will be the integer part of the answer. Then we also have a fractional part, so corresponds to the remainder part. This formula has some special property you can see. If you want to find the common factor between m and n, common factor, okay? So we know common factors in a fraction, you can cancel out, right? Common factor, And we know the quotient part, this integer, won't affect the common factor part, okay? No matter the common factor, large or small, because this is the integer part, it won't impact the common factor part, okay? Then the common factor of r and n will be the same as the common factor of m and n. So it's like this integer part is gone, okay? So that's the observation we need to have from this formula transformation. So when we go back to the GCD version, so you can see based on this observation in this formula, we can cross out this NQ part, okay? Because NQ part, that's the multiple of this divisor n. It won't impact the common divisor of those two variables. So we can remove it. Now, after remove that NQ part, you can see we get a GCD of two numbers, n and r, and this time the problem size is reduced. So we do the problem size reduction in this way. Okay? So this formula gives us the problem size reduction. Okay? So we get size reduction. Remember, the size corresponds to max of the two numbers n and r. We know r strictly less than n, right? So that is n, right? It is reduced. Comparing with the max of m and n, it is reduced. Okay? All right. And next, we can keep doing this. Because for this GCD, can we do another round division algorithm, quotient, remainder, reduction, another round? Okay? So you keep doing this again and again, and finally you will get to an answer that you cannot reduce the size anymore, so you get the answer. That's the idea. So problem size reduction idea. Because sooner or later, your reduction procedure will converge to one particular number, and you can never reduce anymore. Then you're done. Okay, the whole process is done. Yeah. All right, let me show you a simple example. Still, our original example, 60 and 24. Yeah, our high school example. Yeah, but this time we use the division algorithm. Okay, quotient. This is the quotient. This is the remainder R. Okay, but we drop the quotient part. We do reduction. So 24, 12. But 24 is a multiple of 12, right? Multiple of 12. So after the reduction, so multiple of the divisor reduction, you can remove multiple of divisor, right? So you get 12 and 0. When you have 0, remember, if one variable is 0, the other non-zero, the GCD is just that non-zero number. So then we are done. Okay? So this method, we can also solve the GCD problem. But this method, comparing with the solution number 1, the first one, so you can see the biggest advantage is when we do integer division, it is very fast. Even for thousands of digits. Remember, we tried to solve GCD with two numbers with thousands of digits. Even for that huge numbers, we can still do integer division extremely fast. Extremely fast. Lightning fast. Fractional of second fast. Okay, so we can find this GCD extremely fast because we do not rely on prime factorization. That is extremely slow. Okay. All right. So that's the main point. Yeah. All right. Next, we want to implement. Yeah. Because at the end, we want to write a function, recursive function, to find the answer. Yeah. So now let's do it. Yeah. It's pretty straightforward. After we get the, detail step. So we can write it out easily. Yeah. Here, that algorithm is the famous Euclid's algorithm. Euclid's, yeah. More than 20,000 years ago. So this algorithm was written in the book Euclid's famous, the geometry book. Yeah. Yeah. All right. Rule, yeah. Problem size reduction rule. When we find GCD of two integers, x and y. Okay. All right. If y equals 0, but x not equal to 0. Okay. In that case, the answer is x. Yeah. If y not equal to 0, but x mod y equals 0. So that means x is a multiple of y. The answer is y. Otherwise, if not the above two cases, the remaining situation, then first parameter y, second parameter the remainder part. Yeah, modular operator, that percent sign, modular operator, so we get a remainder. All right, so in that way, we reduce the problem size. So if when we start, we have this situation, x greater than y, after this step, this round reduction, so we reduce the problem size using a variable size reduction. Yeah. All right, so at the end, we can write our function in this way, recursive way. Yeah. Three cases, okay? Both 0 will return -1 because no valid number for this given data. Yeah. Then second, our case number 1, then our case number 2, then the last one, recursion. We solve it, last one by recursion. Yeah. So we complete the whole solution. Yeah. All right. So we complete the whole part A of Module 3.